For this problem, we're given the curve with the parametric equations x is equal to t times 1 plus t, y is equal to 1 over 1 plus t, where t is greater than or equal to 0. We're told the region R is bound by the curve, the x-axis, the lines x equals 0 and x equals 2. Find the exact area of the region R as shaded in this diagram. So we need to do a little bit of work for this. There's quite a few stages. First of all, we want to find the area. So normally we'd be integrating, and we are given some limits in terms of x, 0 and 2, and we would integrate our y expression with respect to x, and that would be fine. However, unfortunately for this problem, our y is in terms of the parameter t, our x is in terms of the parameter t, so it's not quite as simple. So what we need to do is we need to modify this and say really we're going to integrate y times dx by dt. But in doing this, we now have a problem because our limits have now changed, because our limits will be in the variable t rather than the variable x. So we're going to need to find those. We're also going to need to find an expression for dx by dt, and then we're going to need to put those together in order to be able to integrate the function. So let's start off by trying to find our limits then. Well, we're given limits in terms of x, and we're given an expression for x. So let's put those two things together. When x is equal to 0, we can say that t times 1 plus t is equal to 0, which is already factorised for us, which is really nice. So t is equal to 0, t is equal to minus 1. However, we're already told in the opening line that t must be greater than or equal to 0, so we can discount one of those limits. So as t is greater than or equal to 0, this implies that t is equal to 0. So matching it up, that becomes our lower limit. Similarly then, we also need to say when x is equal to 2, and we're going to set our expression, so t times 1 plus t is equal to 2. Now this is a little bit more complicated because we do actually have to expand here and make it into a quadratic. So we've got t squared plus t minus 2 is equal to 0, which we can then factorise. So we've got t plus 2, t minus 1. So therefore t is equal to minus 2, t is equal to 1. And the same argument as with the last limits, as t must be greater than or equal to 0, that implies t is equal to 1, which becomes our upper limit. So you cannot just assume that they're going to be the same numbers for both x and for t. They're very likely to be different. So in order to generate this then, we have our expression for y, so we can substitute that in terms of t, but we do need to get an expression for dx by dt. So if we look at our x expression, let's just expand that, so t plus t squared. If we differentiate that with respect to t, we get 2t plus 1 for our answer, so we can now substitute these in. So between our limits of 0 and 1, we have our y, which is 1 over 1 plus t, times our dx by dt, 2t plus 1, which actually we can bring those together to say that we have 2t plus 1 over t plus 1, which we're going to integrate with respect to t. And this is when we've got to spot there's another problem here, which makes the problem a little bit more difficult, that the highest power of t in the numerator is equal to that in the denominator, so actually we have an improper fraction. So before we can integrate our improper fraction, we need to use algebraic division. So we're going to divide 2t plus 1 by t plus 1. 2t divided by t is 2. Multiplying it out, you get 2t plus 2. Subtract those, 1 minus 2 minus 1. The highest power of t here is less than it is here, so we can stop. So actually, we're going to integrate between 1 and 0 of 2 minus 1 over t plus 1 with respect to t. So we can do this integration now, which gets us 2t minus the natural logarithm of t plus 1 between 0 and 1. We can substitute in our upper limit first. So we have 2 minus the natural logarithm of 2 minus 2 times 0, 0, minus the natural logarithm of 1. Natural logarithm of 1 is also 0, so that entire second bracket just goes to 0. So we get our answer there of 2 minus ln2. And that's what we get for the exact area of the region R.